Hello. So this video is going to go over a problem that really deals with Invnorm and sampling distribution for proportions. So let's take this example. About 7% of the world's population has hazel eyes. Suppose we take a random sample of 150 people. What's the probability that the sample percentage or the sample proportion, that's a p-hat, of people who have hazel eyes is between 6.2% and 8.1%, understood in the sample that you take? All right, so the trait is that you have hazel eyes or not. This is the trait. That's a yes/no trait. Right? Now, just the world's population, that is the population. It's all people. And then 7% is P. It's the percent of all people that have the trait, that have hazel eyes. And then here we have 150 is the sample size. Okay? Now, from the theory, as long as we meet conditions, and we can do that kind of quickly, we can assume this is a random sample. 150 is certainly less than 10% of all people in the world. And out of 150 people, if 7% have hazel eyes, let's just do that real quickly. That's exactly 10 and a half people. So we just meet conditions. 10 have the trait, and then the rest, 140, don't. So we meet conditions. So what that tells me by the theory is that my samples will pile up around 7%, right, the mean, P, and it'll spread out by the standard deviation formula. So the standard deviation formula for my samples, how my samples will spread out, is, remember, 0.07, 1 minus 0.07 over 150, and that's 0.021, right? So what that means is if I round to 0.02, just to kind of make it a little easier, this would be 0.09, 0.11, 0.13, 0.05, 0.03, and 0.01. And remember, that means that these are my p-hats, right? They're piling up. I take samples, and my samples cluster around the truth, right, like this. And what happens is, if you've got so many samples here, 68% of my samples are going to have between 5 and 9% people who have hazel eyes in those samples. 95% of my samples are going to have between 3 and 11% people in those samples that have hazel eyes, and so on and so forth. So let's say here the question is, well, what's the probability that when I do take a sample, I'm going to get a sample somewhere between 6.2% and 8.1%? Well, 6.2% is somewhere between 5 and 7%, so we'll say it's somewhere just a little bit past halfway. So what's the chances I get a sample percent between 6.2% and 8.1, which would be somewhere here? So I want to know what's the chance I get from, let's say, here to here, a sample percent from here to here. Right? That's really what I want to know. Right? So all I have to do is find a z-score for each one of these sample percents or sample proportions, and then find the area in between that. So here we go. Here's the z-score for 0.062. How far is that sample value, right? That sample value from the mean standardized, right? Which in our case is going to be how far is p-hat from p divided by the standard deviation of the sample proportions. So that's going to be how far is 0.062 from 0.07 divided by 0.021. And we're going to get negative 0.3810. Let's see if you all can see that. Yeah. So that's the first one. I'm going to shorten this up. I just wanted you to see what this would be. And the second z-score for 0.081 is going to be how far is 0.081 from the mean 0.07, right? Divided by 0.021. And I'm going to get that it's 0.5238 standard deviations from the mean. Now what that means is, remember, here's 0.07, it's 0 standard deviations. This is -1 standard deviation. Let me write that in there. This is 0 standard deviations, this is -1, this is +1, right? This is +2, +3 standard deviations, -2, -3 standard deviations. And what we're saying is the sample proportion we're looking for, 0.062, is about negative 0.3810, not even half a standard deviation away, and this one is about half a standard deviation away. All right, so now we find the area under the curve, and from negative 0.3810 standard deviations to 0.5 238 standard deviations, and you should get 3482 or 34.82%. Right? Now, how do I write that sentence? Well, what that means is, let's take this out, about 34.82% of all sample proportions or sample percents will have somewhere between, right, 6.2% and 8.1% people with hazel eyes. Okay, so remember, it's easy to get a little bit confused. This percent measures how often the trait occurs in the sample. So it's occurring pretty low, right? 6%, 8%. That's not many people in my sample. So that means about 6 out of every 100 people or 8 out of every 100 people have the trait of having hazel eyes. But the chances of getting those samples is reasonably high here, it's almost 35%. So that's what that question's asking. How often will you get some sample proportions like that? Now let's take a look at the next question. The probability is 75% that the sample percentage is within symmetrical limits of the population percentage of people who have hazel eyes. So this is asking you that basically, if you're within symmetrical limits, when you look at the normal curve, right, the population percentage is 0.07. We know 7% of all people have hazel eyes. And the symmetry really arises from the fact that you have this normal curve that's symmetric. So what is this 75%? So if I'm telling you there's a 75% chance of getting the sample, I want to know what sample is it that I would get. So what we were saying is symmetrically located about the population proportion. We're going to be capturing 75% of those sample proportions, and we want to know what are those sample proportions. So if you divide 75 by 2, right, 75 divided by 2, because I want the symmetry, half on one side of the mean, half on the other side of the mean, you're going to get 37.5%. Okay, so that means I have 37.5% on one side of the mean, 37.5% on the other side of the mean, and I'm basically saying I'm capturing that much area under the curve. But what would that correspond to? What p hat would that correspond to? And what p hat would that correspond to here? Okay. So, and notice the clue is that it's the probability. Remember the probability of getting this sample? Then you want to know how much is this trait occurring in my sample. All right, so this is an Invnorm problem because you really want to know, well, okay, how far is this sample from the mean? What is its z-score? So you say, how far from the mean is this p hat located? Right? Well, that's basically looking for a z-score. So we can use Invnorm. Now remember, Invnorm always assumes you have area to the left. So what is the area to the left here? Well, we know from dead center all the way back is 50%, right? So, and we know this piece is 37.5%. So if we subtract 37.5% from 50, we're going to get 12.5%. So this is 12.5%. That means that the area to the left of this position is 12.5%. And so now I want to find the Invnorm of 12.5%. That'll give me the z-score that I'm looking for. And I get negative 1.1503 standard deviations from the mean. All right, so now I can use my z equals value minus mean over standard deviation, right? But now my value is p hat, my mean is p, which is 0.07, and the standard deviation in this particular problem is 0.021. So I'm going to have negative 1.1503, and here is the value I'm looking for, which is a sample proportion. The mean is 0.07, and 0.021. So when I multiply 1.1503 times 0.021 and then add the 0.07, right? So negative 1.1503 times 0.021 plus 0.07 is going to give me my value. I'm going to get 0.0458, which means the sample percent is 4.58%. All right, and then when you do the other side, you're doing the same thing, except that now the area to the left is, right, which is basically how I'm going to find out how far I am from the mean. So I want that z-score. To find that z-score, I have to use Invnorm. Invnorm mandates that I'm looking for area to the left of that position. So area to the left is 12.5% plus the 37.5 plus another 37.5. Right. So it's going to be a total of 87.5%. So now if I do Invnorm of 87.5%, guess what I'm going to get? Same thing I got here, but positive, right? I'm going to have positive 1.1503 standard deviations. And so, of course, if I set this up, I'm going to get 1.1503 is, how far is my value from 0.07 divided by 0.021. And when you do all those calculations, you're going to get 0.0942. So 9.42% is my sample percent. So basically when I take sample percent, so when I look at my sample percents, the ones that are between 4.58% and 9.42% people who have hazel eyes in those samples, that occurs 75% of the time, right? Symmetrically. And by symmetrically, you could say the middle 75% or the central 75% of all samples will have between 4.58 and 9.42% people with hazel eyes. So let me write that down. So you could say the central or middle 75%, you could say symmetric, sample percentages and middle from the population proportions will have between 4.58% and 9.42% people with hazel eyes. Okay? All right, so let's take a look at the third question then. It's very similar. The only difference is before you were asked for 75%, now 94%. So I'll pause. Why don't you pause and see if you can go ahead and do this, right? And basically it would be the same idea. You'd have 0.07 is the population proportion P, and you're looking for 94% symmetrically located or centrally located. So you'd have 47% here, 47% here, and when I say here, I mean all the sample proportions, the p hats that are piling up. 47%, that's an awful, on one side and the other. 94% is almost all of your sample proportions. And so you want to know what would be this sample proportion, what would be that sample proportion, right? So p hat equals what? P hat equals what? Now obviously this, if this half is 50%, then the area to the left of this position is 3%. So I'm looking for that p hat, which has 3% area to its left. So I'm going to use Invnorm. And I get negative 1.8808 standard deviations. And when I set that up to solve for the p hat, right? How far is it from P? Now normally I say value, like sample value minus mean over standard deviation. I'm just getting a little accustomed to the notation here, right? Oh, actually this could be Z really. Should be Z. So negative 1.8808 is some distance from 0.07 here, and then 0.021. So my z-score is 1.8808 when my sample percent that I'm looking for, its distance from the mean standardized, is this z-score. So now when you solve that, you're going to get p hat is 0.0305 or 3.05%. Now, instead of doing this whole thing again and, you know, adding the percentages and basically saying Invnorm of 97% or 0.97, you could say, well, gee, this is symmetric, right? So how far is 3.5%? So let me use a different color here. We got that this was, p hat is 3.05%. We know p is 7%, so how much lower is that? So if you said 7% minus 3.05% is a difference of 3.95%. Well, since this is symmetric, I should be able to add 3.95% to 7% and get this p hat. And indeed you can. So if you do 7% plus 3.95%, you're going to get 10.95%. This one is 10.95%. Okay. Or you could do the whole Invnorm, you know, calculations. You can do that to check yourself if you'd like. So basically, 94% of the centrally located sample percents are going to show that between 3.95 and 10.95% of the people have hazel eyes. Right? That's the idea there. And lastly, part D, if you increase the sample size to, oh, actually we're going to change that from 350 to 1,000. I wanted to make that a lot more obvious. What effect will this have on the probability of getting sample percentages between 6.2% and 8.1%? And those are the ones that we originally found. That was in part A. So I'm using the same p-hats, 6.2%, 8.1%. Right there. Well, before we found that when we only had a sample size of 150, our standard deviation was about 2%. It's actually 2.1%. So we had a little bit more spread. What happens is when you have 1,000, a sample size of 1,000, you're going to have less spread. So how does that look? Now I pre-drew this because it's very hard to draw. So even so, if I had a better scale, this would come out a little bit better. But with a standard deviation of 0.021, because the sample size is smaller at 150, your distribution is more spread out, right? But when you have a sample size of 1,000, your standard deviation goes down from 0.021 down to 0.008. Now your distribution tightens up, becomes more like a spike. And so these same positions, although I could hardly really draw it that well, are now not as far, further away from the mean, because each standard deviation is smaller. So now if you take that same 0.062, how far is it from 0.07? Because the standard deviation is smaller, now this sample is actually going to be further away. And if you compare it, before 0.062 was not even like a half a standard deviation away. It was like negative 0.4 standard deviations away. Now it's a full standard deviation away. And then 0.081, right, 8.1%, was about half a standard deviation away in the positive direction. But in this new distribution, because of a larger sample size and smaller standard deviation, this is over a standard deviation away. It's almost 4 standard deviations away. So now what you're capturing is, you're saying about 75%, right? 75% of all your sample proportions are now going to be captured here between these sample percents, 0.06, 0.062 and 0.081. Whereas before, it was only what? About 34%. And that's because of the standard deviation. Your distribution got a lot tighter, so those same values seem like they are farther away, but it's because the standard deviation got a lot smaller. Okay? All right, thanks for listening.